Welcome. This is a time series analysis course. My name is Nicoleta Serban. I'm Associate Professor in the Stewart School of Industrial and System Engineering. This lecture is on basics of time series analysis. And for this lesson, I will focus on basic definitions of time series, and I will illustrate these concepts with a few examples. What is a time series? It is a sequence or collection of random variables with some similarity in terms of the probability distribution called a stochastic process. For a time series, the sequence of random variables is indexed by time. We commonly refer to a time series as both the stochastic process from which you observe and the realizations or observations from the stochastic process. It's important to highlight that the time series data is our observations in practice, and thus come with uncertainty. There are many examples in which data are correlated in time. The examples on the slides are just a very small subset of examples. Time series data arise in any field, from economic data to finance to healthcare to climate, among many others. The level of time granularity from yearly to minute depends on the objective of the problem at hand. The time granularity also depends on resources needed to observe the time process of interest on the smoothness of the time process as it changes over time. A first example on this slide is the U.S. yearly GDP. The second example is the monthly sales of wine. A third example is the monthly accidental death in the U.S. A fourth example is the monthly interest rate. Often yearly and monthly data are observed over several years, tens of years. A fifth example is the daily average temperature. A sixth example is the daily stock price of a company such as IBM. Ideally, we'll observe daily data as it allows us analysis of multiple other resolutions, since daily data can be aggregated into weekly data, monthly, or yearly data, depending on the objective of analysis. But sometimes we have data at even more granular time, for example, the minute or even a second. For example, 1 minute intraday as S&P 500 return. More generally, the level of time granularity and the time series model to be considered in drawing inferences on a time series process depends on the characteristics of the time series. One very important characteristic is the trend. The trend can be a long-term increase or decrease in the data over time, or it can fluctuate smoothly or non-smoothly. Seasonality is influenced by seasonal factors, quarter of the year, month, or day of the week. When seasonality repeats exactly at the same time intervals and with exactly the same regular pattern, we have periodicity. But there could be other cyclical trends that do not repeat over similar or the same periods of time. Cyclical trends are when data exhibit rises and falls that are not of a fixed period. For some time series, we can observe heteroskedasticity, which means the variability in the data changes with time. For example, financial indicators of companies that have been around for decades will be less variable in the early years, but more variables in the recent years. Last, the correlation with time can be positive. In other words, successive observations are similar, or negative. In other words, successive observations are dissimilar. Let's look at a few examples of time series. Here is the plot of the gross domestic product for the U.S. The trend is clearly increasing monotone. There is no seasonality, periodicity, or cyclical trends. The variability of the observations does not change over time. Here is a plot of the close price of the stock for IBM, where IBM is a company standing for International Business Machines. The trend is overall monotone increasing with fluctuations in the later decades. There is no clear seasonality that can be evaluated visually. This is not uncommon when looking at daily data. However, what is clear is the heteroscedasticity of the time series. The variability in the stock price clearly shows a big change from being significantly smaller in the early years versus much larger in the later years. Data on a much lower granularity than day, week, or month is common in some fields, including in high-frequency financial data or in patient monitoring, such as cardiac monitoring using EKG technology. This is an example. Here is the S&P 500 intraday stock return. We can see that the intraday data is very different from one day to another, with much variability in some days than others. But why do we need yet another set of statistical modeling tools to model time series data? The main reason is that the time series response data are correlated. This correlation results in a much smaller number of degrees of freedom than otherwise assumed under independence. Moreover, because of the correlation, the data are concentrated into a smaller part of the probability space where the data lie. Ignoring dependence leads to inefficient estimates of the parameters in a model. It leads to poor predictions, to standard errors unrealistically small, in other words, leading to narrow confidence intervals, thus improper statistical inferences. In time series analysis provided in this course, we'll focus on several objectives. First, we'll perform a descriptive analysis, for example, plot the data and obtain simple descriptive measures of the main properties of the time series. Second, we'll explain the time series, particularly the dependence in the time series, through finding a model that will describe appropriately the dependence in the data. This objective relies heavily on the first step, the exploratory data analysis, since this first step can provide insights on the type of dependence in the data. Modeling the time series by capturing the properties of the time series is important for the third objective, forecasting and prediction of future realization of the time series data. Last, it's often the case that the modeling and forecasting will provide additional insights about the behavior of the time series, suggesting some tuning of the model. I will illustrate all these objectives with several data examples in this course. Last, I will point out that the time series modeling divides into two types of modeling: time domain approaches and frequency domain approaches. In the time domain approach, we assume that the correlation between adjacent points in time can be explained through dependence of the current value on past values. In the frequency domain approach, characteristics of interest related to periodic or systematic periodic variations in the data are often caused by biological, physical, and environmental phenomena. All the models introduced in this course are in the time domain, but it's important to remember that the area of time series modeling is much broader than provided in this course. To summarize, in this lesson, I provided basic definitions of time series illustrated with a few examples. Thank you. Welcome. This is a time series analysis course. My name is Nicoleta Serban. I'm Associate Professor in the Stewart School of Industry and System Engineering. This lecture is on basics of time series analysis. And for this lesson, I will focus on the presentation of the basic decomposition of a time series. And I'll provide two approaches for estimating one component, the trend. This slide is to provide a snapshot of the basic modeling of time series. For the simplest time series analysis, the response data are Y, T, the time-varying observations, where T is the time index, for example, day, month, week. In order to account for trend and seasonality or periodicity, We decompose the time series into three components, MT, ST, and XT, where MT is a trend, ST is the seasonality, and XT is a time process after accounting for trend and seasonality. XT is often assumed to be a stationary component. In other words, its probability distribution does not change when shifted in time. Most classic time series models assume that the time process is stationary, and thus we need to first estimate the trend and the seasonality components, subtract them from YT, then further model XT. Note that XT is not an error term. In this lesson, I will describe common approaches for estimating the trend. Since most time series have a trend, in the basic time series model, we first will remove the trend, then model the residual stationary process if there is no seasonality. We can estimate the trend using two approaches: estimation of the trend, then removing it from the time series, or differencing the data, which directly removes the trend. I generally prefer the first approach, since estimating the trend allows us to gain more insights about the behavior of the time series. However, if we do not have a good model for estimating the trend, then the residual process after removing the trend may not be fully trend-free and thus not stationary. The three approaches commonly employed to estimate the trend in a time-varying process or a time series are the moving average approach, parametric regression, or non-parametric regression. The moving average approach is the simplest estimation method. In fact, it is a non-parametric approach. In moving average, we estimate the trend at the given point MT by taking the average of the time series values within a neighborhood of MT. First, we need to establish the width of the moving window, defined on the slide with D. If D is, the average depends on whether D is even or odd. The selection of the width in the moving average is important since it's a calibration parameter controlling the bias variance trade-off. If it is too large, then the estimated trend is very smooth, that is, has a low variability but high bias. If it's too small, the estimated trend is not smooth, that is, has high variability but low bias. For moving average trend estimation, this is the most challenging part. On another note, for those who have a broader understanding of statistical modeling, the moving average is a particular case of kernel regression when we use a kernel with equal weights. We can also use a standard linear regression to estimate the trend. We can define the trend as a polynomial of order p, where the betas will be the regression coefficients. The most common polynomial trends are with p equal to 1 or p equal to 2. For higher polynomials, it is better to use non-parametric regression, particularly if p is not known in advance. Generally, in this approach, we estimate the betas using the linear regression approach you have learned in the regression analysis course. For this, the predicting variables are t squared, t cubed, and so on up to t to the power p. If p is large, one could also employ model selection to select which of the terms in the polynomial should be included for a good fit. However, this needs to be considered with caution, since the terms in t, or the predicting variables in the regression model, are highly correlated. Alternatively, if we do not know p, or we do not know which terms to keep in the polynomial, we can use non-parametric regression, which does not make any parametric assumptions. The simplest approach is kernel regression, which is a linear smoother, which looks like the one on the slide. The function LIT depends on the kernel function in kernel regression and can be viewed as weights in local moving average. Recall that I mentioned earlier that moving average is a particular case of kernel regression. Another approach is local polynomial regression, which involves fitting a polynomial within a moving window at each time point. Kernel regression is a particular case of this approach. Last, there are many other approaches, for example, nonparametric regression using splines, wavelets, or Fourier orthogonal functions. But which one to choose among so many approaches? Local polynomial smoothing usually performs better than kernel regression on the boundaries and is not biased by the selected design of the time points. Other methods can be selected depending on the smoothness level of the function to be estimated. For example, wavelets are adaptive to less smoothness, but generally for estimating trends in time series, local polynomial smoothing or splines regression will perform well. To summarize, in this lesson, I provided some basic methods to use to estimate the trend. Thank you. Welcome. This is a time series analysis course. My name is Nicoleta Serban. I'm Associate Professor in the Stewart School of Industrial and System Engineering. The lecture is on basics of time series analysis, and for this particular lesson, I will illustrate the estimation of trend using a series of data examples. I will illustrate trend estimation with the time series of the average monthly temperature in Atlanta, Georgia, where Georgia Tech is located. The data are available from the iweathernet.com. The Weather Bureau, now the National Weather Service, began keeping weather records for Atlanta since October 1878 for more than 138 years. The data for this example is starting with January 1879 until December 2016 to have 138 complete years of data. The temperature values are provided in Fahrenheit degrees. The question we like to address is, did the temperature increase over the past 138 years? If yes, by how much? To begin the analysis, we'll first need to read the data file in R. We'll use the R command read.table, where the input in the file is the data file called avtemp.atlanta.txt. I also specified that the data file has a row with the names of the columns, and thus header is equal to T, or true. Now the data object in R is a data frame. In order to learn about the columns in the data, we can use the command names data, where the output is here. According to this, the first column provides the year. The next is the average temperature for January in each of the year. The second column is for February, and so on. We also have a column with the annual average temperature at the end. To get all temperature values in one vector, I use the command asVector, which takes a matrix and stacks up the columns in the matrix into one vector. However, we want to stack up the rows, not the columns, in order to keep the temporal order of the data. For that, I took the transpose of the matrix of the data using the T command in R. In the transpose, the rows of the initial matrix are now columns, and thus we can use the asVector command. Note that I discarded the first and the last column in the data matrix, since those correspond to year and annual columns. Last, I converted a vector of temperature values into a time series using the tsr command, with the specification that the first year is 1879 and that these are monthly observations, thus frequency equal to 12. The plot of this time series can be displayed using tsplotr command. The plot is here. As expected, there is seasonality. We will explore this in the next two lessons. The range of temperature values goes from as low as 30 Fahrenheit degrees to as high as 85 degrees. Note that those are average monthly temperature and thus not capturing some extreme temperature values. Looking at this plot alone is difficult to identify a trend over time. We'll employ the estimation approaches for trend discussed in the previous lesson. We'll begin with estimation of the trend using moving average. I first define the vector of time points. Because the time points are equally spaced, because this is monthly data, I can simply consider the time domain between 0 and 1 with the time points in this time domain equally spaced, as the R code on the slide provides. Next, I use the K-smooth R command, which is used for kernel regression. Note that I mentioned in the previous lesson that moving average is a particular case of kernel regression where we use a constant kernel within the moving window, which in this case is called box kernel. Thus, specifying kernel equal box in this R command will give us a moving average estimator of the trend. With the TS command, I transform the fitted trend into a time series, then plotted, overlaying on top of the observed time series using the lines command. I also added the constant line to compare the fitted trend with the constant line using the app line command. The plot is here. The purple line is the fitted moving average trend and the blue line is the constant line. From this plot, we see a slight increase of the trend and compared to the constant line, although it is hard to notice the difference since the variability of the data is large as compared to that of the estimated trend. For fitting a parametric regression model, we can use the LM command in R, used for fitting a linear regression model. The predicting variables are the linear and quadratic time points. In the LM command, we specify the time series on the left, which is the response data in fitting the linear regression model. And on the right, in this command, we have the two predicting variables. With this, we fit a quadratic trend. The summary R command provides information about the model fit. Here is only a portion of the output of the model fit. This shows the estimated coefficients along with inferences on the statistical significance of the coefficients. From this output, each of the coefficients corresponding to the two predicting variables are not statistically significant because the p-values are large. Similar to the moving average trend, I use the TS command to transform the fitted values based on this model into a time series. I use a similar approach to plot the trend against the observed data. The plot is here. The green line is the fitted trend and the blue line is the constant line. From this plot, we also see a slight increase of the trend as compared to the constant line. On this slide, I'm providing the R commands that can be used to fit a trend using local polynomial regression and the splines regression. The common function used to fit a local polynomial regression is LOES. The input consists of the time series on the left and the time points on the right. Once that fitted, we can transform the fitted values using the TS command into a time series. For splines regression, there are many R libraries and commands that can be used. I generally prefer using the GAM command from the MGCV library because this R command is flexible in terms of the type of the model to be fitted. Using this command, we'll need to transform the time points using S of the time points to specify that I want a splines fit. If we do not specify this, the GAM will fit a linear model in the time points. Similarly, I transform the fitted values of this model using the TS command. Next, I overlay the fitted trends from the two models to the observed time series. The plot is here. In this plot, it is less clear whether there is an increasing trend over time. Last, I'm comparing the estimated trends based on the 4 approaches: moving average, parametric quadratic regression, local polynomial regression, and splines regression. This time, I only plotted the trends to see clearly the difference in the fitted trends. The first 2 command lines are to provide the scale of the plot such that all the trends will be plotted on the same scale. Then I plotted the trends along with the langed commands, which allows identification of the lines with the corresponding trend estimation method. The plot is here. From this plot, we see that the moving average trend is quite weakly, slightly capturing some of the seasonality, thus not a good estimate. The estimated trend using the parametric model is comparable to that fitted using the splines regression, except that the parametric fitting model is slightly quadratic, but generally both capture a similar increasing trend over time. The fit using local polynomial regression shows more complexity in the trend, with some smooth ups and downs, although generally it also shows an increase in the temperature over time. Generally, from all 4 approaches, we see an increase in temperature with about 2 degrees in the last 138 years. To summarize, in this lesson, I illustrated the trend estimated approaches using a data example. Thank you.